Hello everyone, I am Ritika Sunskar, Assistant Professor IT Department. So in the course of Artificial Intelligence, we will discuss about Unit 3. So Unit 3 is based on knowledge representation and reasoning, where we already discussed about reasoning under uncertainty. So in the knowledge representation technique, there are three types. The first thing is the probability, second thing is the truth maintenance system, and third thing is the fuzzy logic. Okay, so we already discussed about the probability, conditional probability, and we also discuss about the truth maintenance system, and in previous video we discuss about the introduction part of the fuzzy logic. So in this video we will discuss about the fuzzy propositional logic and inferences rule in the proposition logics. So let us discuss here. The first thing is the classical logic.
The classical logic. Okay. Logic is used to represent the simple facts. The logic defines the simple way of putting symbols together to form a sentences that represent the facts. The sentences are either true or false, but not both are called as a propositions. Okay. So the example is if we are having the sentences truth table and it is a proposition or not. Okay. So the logic is in the form of a yes or a sentence is either true or a false, or we can say that yes or no. So we have one sentence over here: grass is a green. Okay. So truth table is a true. So it is a proposition. Yes. 2 plus 5 equal to 5, then truth value is a false, then it is a proposition. Yes. Close the door. Okay. So here we are not getting the value in the form of true or a false. Okay. We can't say the answer is true or a false. Okay. So it is a proposition. No. So is it hot outside? Okay, here is also answer is in the form of a null value. Okay, we are not find out the answer is true or false over here. Okay, so it is a proposition. No. X is greater than 2. So here we are not defining the value of a x. Okay, so we can't say the answer is true here. Here x is greater than 2. Okay, so it may be true or it may be false. So truth value is a null over here. So it is a proposition. No, x is not defined. Okay, similarly for x equal to x, truth value is null because we are not defining the value x here. So truth value is a null, not true or not false. So it is a proposition. No. So the sentence are either, so here the sentence are in the form of true or false, but not both are called as a proposition. So in this close the door, it is hot or outside, x is greater than 2 or x equal to x. We cannot decide the value is true or false. So it is a not a proposition. Okay. Then proposition logic. Okay. So in a classical logic, the concept, the another concept is a propositional logic. So propositional is a statement which which in English is a declarative sentence, and logic defines the way of putting the symbols together to form a sentences that represent facts. So the every proposition is either true or false, and proposition logic is also called as a Boolean algebra. Okay. Proposition logic is also called as a Boolean algebra, that the operations are based on Boolean variable, that is true or false. So the example, so sky is a blue. Okay, so this is also the proposition. Snow is a cold, and 12 into 12 equal to 144. So this is all this kind of all the sentences are in the form of proposition logic. So answer is true. So here the answer is also true, and here the answer is also true. So all these answers are true, then it is a proposition. So the next is a proposition logic. It is a fundamental to all logic. Propositions are sentences, either true or false, but not both. Okay. So the propositions are in the form of true conditions or either in the false condition, but not both. Okay. So sentence is smallest unit in the propositional logic. If the proposition is true, then the true value is a true, else false. Truth value is a true and else false. So the example sentences, grass is a green, truth value is a true, proposition is yes. Okay, here also. So both these two sentences, above two sentences are proposition and rest of the sentences are not the propositions. Clear? Then in a proposition logic, there are statements, variables, and symbols. Okay, so what is a statement? So, simple statement is one that does not contain any other statement as a part. A compound statement is one that has two or more simple statements are called as a components. Okay. So in a statement, there are two types of statement, simple statement and compound statement. Only one that does not contain any other statement, it is called as a simple statement. And one that has two or more simple statement are called as a compound statement. Or we can say that it is called as a components. Okay. Then the second part is a operator or connective. Okay, so join simple statement into the compound and joins compound into the large compounds, it's called as a operators or connectivity between the two statements. Then the proposition logic contains symbols for connectivities. Okay, so these are the all symbols. By using these symbols, we have to we can combine two statement, that is simple statement also or compound statement also. So the symbols for connectivity is the assertion P is a true. So negation, if we are having the P statement, okay, so P is a statement over here. The assertion is a P, so P is a true. Okay, we are applying the negation of P, so not operator. Okay, so these are the all negations. P is a false. Okay, if we are applying the statement in the form of negation symbol, so the statement become false. Conjunctive P and Q. So this is also the symbol for the conjunctive dot operator, and or we can use the and symbol only. So both P and Q are a true. Here we are using the two statement, P statement and Q statement. Here we are combining the two statement by using the AND operator or a conjunction operator. For the disjunction P or Q, so this is the symbol for OR and this is also symbol for OR, and OR either P is a true or Q is a true or a both. Implication P implies Q, so this is a symbol for implication. This is also the symbol for implication. If then, okay, so if P is a true, then Q is a true. P implies Q. Equivalence, so this is a symbol for equivalence, so this is the also symbol for equivalence, three lines, and this is also symbol for the equivalence, if and only if. So P and Q are either both true or both false. Okay, so these are the all the symbols for connectivities between the two statements in the propositional logic. Then the classical set or a crypt set. Okay, so in the previous slide we discussed what is the classical logic, and in the second slide, next part is a classical set, or we can say that it has a crypt set. So the classical set is a collection of distinct objects. For example, a set of students passing the grades. The each individual entity in a set is called as a member or an element of the set. So the classical set is defined in such a way that the universe of discourses is the splitted into the two groups, members and non-members. Hence, in case the classical sets, no partial membership exists. So let A is a given set. So in this diagram, A is a given set. The membership function can be used to define a set A is given by mu A in bracket x equal to, if x belongs to A, then answer is 1, and if x is not belongs to set A, then answer is a 0. Okay. Next is the operations on classical set. So there are multiple operations performed in the classical set if you are considering the two sets, A set and B set, and universe is a X. Okay, so The first is a union, A union B. So X is belongs to A or X is belongs to B for all X. So this operation is called as a logical or. Similarly for AND, A and B, or we can say that intersection B, X belongs to A and X belongs to B. Similarly for complement, X is not belongs to A and X is belongs to X, that is universe. Okay, so this is the complement of A. Differences, X belongs to A and X is not belongs to B. Okay, so this is the symbol for the difference, A uh, oblique B. Then the properties of classical set. So these are the some properties for the classical set: commutativity, associativity, distributivity, idempotency, identity, and transitivity. Okay, so in a commutativity, A union B is equal to B union A, and in the second, A intersection B is also the B intersection A. Similarly, for associativity, A union in bracket B union C is equal to A union B union C, and similarly for the intersection also. For the distributivity, A union in bracket B intersection C, so we can write it as A union B intersection A union C, and vice versa for this second line also. A intersection in bracket B union C is equal to the A intersection B union A intersection C. Idempotency, if we are having the A union A, set A union A equal to A, and for set A intersection A is also A. Then idempotency, A union null value is equal to A. A intersection universe, that is X equal to A. A intersection null value is equal to null, and A union X equal to X, that is universe X. Then transitivity, if A is a subset of a B and B is a subset of a C, then A is also the subset of a C. Okay, so this is the transitivity. Okay, so these are the all the operations performed on the classical set or a Cripps set. Fuzzy propositional. So in a fuzzy proposition is a statement P. Okay, we have considered one statement, that is P, which acquires a fuzzy truth value. Okay, the fuzzy truth value. So we are denoting the fuzzy truth value T in bracket P. So truth value of a statement P. So example, P equal to Ram is honest. Okay, we have one statement over here. So Ram is honest. So the truth value for this particular statement is 0.8. It means that P is a partially true. Okay. So if you are getting the truth value for this particular statement, P is equal to 1, it means that P is a absolutely true. Okay. So this is a fuzzy propositional. Next, so in a proposition logic, there are some inferences rule present. Okay, so in a proposition logic, there are two types of inferences rule. First one is a modus ponens rule, and then second one is a modus tollens. So first we discuss what is a modus ponens. Okay, so the modus ponens rule is one of the most important rule of inferences, and it states that if P and P implies Q is a true, P is also true and P implies Q is also true, then we can infer that Q will be true. So it can be represented as in the form of notation of modus ponens. If P implies Q is a true and P is also true, then it will infer that Q is also true. So this is the representation of a modus ponens. Okay, so we are using some example here. P implies Q. It means if I am sleepy, okay, so here, so if I am sleepy, then I go to bed. So here the P is a I am sleepy and Q is a go to bed. I go to bed. So P implies Q. If I am sleepy, then I go to bed. What say the modus ponens rule? So the P implies Q. So this is also true statement if and only if P is also true and Q is also true. Okay, so the proof of this truth table for the modus ponens is we are generating the truth table for the two statement P and Q. So here truth table for 0 0 means false value, 0 1 means false and true, 1 0 means true and false, and 1 1 means true and true. So, what say the modus ponens rule? So, if the P implies Q, if the P is Q and P is a true and Q is a true, then only the P implies Q is also true. Okay. So, in this condition, here both are false here. So, these two values are false over here. Only the last line P becomes one that is true and Q becomes one that is true. And also P implies Q is also true. So this is the modus ponens representation. Okay. Then the another example is we are generating the premises, two premises over here. The premises one that the here the sentence is a x is a and premises two. If x is a then y is a b. So the consequence is that Y is a BO. Okay. So the modus ponens is associated with the implication A implies B. So in term of proposition P and Q, the modus ponens is represented as P and P implies Q. Okay. So in this notation, we are generating the notation in the form of a and. So P and P implies Q in bracket implies Q. Okay, in terms of a modus ponens. Then second inference rule is the modus tollens. So the modus tollens rule state that if P implies Q is a true and negation of Q is a true. Okay, so in the modus ponens we are generating P implies Q is a true, then Q is also true and P is also true. But in a modus tollens, if the P implies Q is a true and negation of Q is a true, then negation of P will also be true. Okay, so it can be represented as P implies Q is a true, negation of Q is a true, and negation of P is also true. So the example in a modus tollens is if P implies a Q is a similar example for the modus tollens also. If I am sleepy, then I go to bed. So here the P statement is that I am sleepy and Q statement is I go to bed. So the negation of Q will be I do not go to the bed. Okay, and negation of P becomes I am not sleepy. So these are the two negation operations, negation statement over here. Okay, so truth table for the proof of a modus tollens become. So here also we are generating the truth table for P statement and Q statement. So the truth table for Q 0 0 1 1 0 1 0 1 and negation P becomes 0 become 1 and 1 become 0, and for the negation of Q 0 become 1 1 become 0 and so on. Okay, so what say the modus tollens rule? If the negation of Q and negation of P will also true. So here the negation statement not we are not considering the P and Q. Okay, we are considering over here the negation of P and negation of Q. So in that the negation P and negation Q both are 1 1. Okay, so in the first line both are 1 1. So then only the P and P implies Q is also 1. Okay, so this first line is a modus tollens representation for the truth table in the truth table. Okay, so but in the modus ponens, so this is the our conclusion in the truth table, and in the modus tollens this is our conclusion. Okay, so then here we also generate the premises 1 and 2 for the modus tollens. So in that y is not b. Okay, so here x is a and y is a b. So the first line is y is not b. If x is a then y is a b. the consequence is generated here, x is not a a. Okay, so here for both y and x we are generating the negation operation. Okay, but in a modus ponens we are creating only x is a and y is a b. Okay, so in terms of proposition p and q, the modus tollens is represented as in the form of a negation here. Okay, so this is for the modus ponens, and in that we are performing the negation operator. Negation of q and p implies q, bracket complete, implies to the negation of p. Okay, so these are the two inferences rule used in a propositional logic. Thank you.